So I got an email from Huggins over the weekend saying, Mr. Holloway, I wish we could have more trig proofs and that it was just a bigger part of class. And I thought about it long and hard and I decided, you know what, Huggins, that's correct. We should do more proofs in here. So, coincidentally, we also happen to be starting Chapter 5, Section 2, where we're not going to say anything about proof. We're going to just talk about how does one verify trig identities. Okay. Verifying trig identities. Now, as we look at these, there is a fundamental thing that we need to make sure that we can all agree on. We have some equations that are only true for certain values. Square root of x equals 5 works for the one number, right? Cool. We have, in contrast with that, things that are true for all possible values. So right off the bat, immediately, we're going to define an identity before even looking at our first section. So in mathematics, when we talk about an identity. Okay, two ways you can think about this. Either the identity is an operational identity, so like 0 is the number that I add to something to get the same number out, or 1 is the number that I multiply by to get the same number out, or we have identities in a larger sense that are simply going to be equations that hold true for all, which maybe an upside down capital A would be a good thing to put in there, for all values. Okay. We have some equations that hold true for every single x or theta, whatever it is that you would ever look at. So our first section is going to be just some basic examples, and really they're just all examples realistically. So what I would suggest is, if you want them, we'll talk about them, but I'm not going to write them all down. Guidelines for verification. Is there a shorter word that you could write than verification? Proof. Okay, we're doing proof, but they're not your ugly geometry proofs that everybody loved so much. A little bit different. Okay, guidelines, first and foremost. Are these like straight up rules? No, they're just kind of some helpful things to go through. Now, couple of these, I'm just going to copy and paste it again. We're not going to take the time to write them all up here. We'll just talk about them. You might be able to get some of them written, but I'm going to focus. Cool, we'll move it down. And here we go. When we're looking at these guidelines, some general pieces of advice that I can offer, but again, they will not always just be perfectly like this. In your notes, if you were to write it, about this long. Now, I would prefer, if you want them, leave 5 spaces with a couple lines in there on a couple of them. But I'd rather just talk about these than you committing all the time to write it down and just ignore what I'm saying. Okay, identities are not equations yet. When we're trying to verify it, because we're checking to see whether or not two things really are equal, or we're verifying that they're equal, you can't use the properties of equality. No multiplying both sides, no doing anything, because you would have to assume that they're equal to show that they're equal, and you can't do that. Okay, Huggins, for these, you do not have to write them right now. However, if you want them in your notes, you should add them, but I don't want to take the time to write them all. Okay, because they're not equations, you can only work with one side at a time. And it's really counterintuitive. Pick the ugly side. There are more things that you can do to an ugly side than there, like more obvious stuff to do than the easy side. Okay, once you have determined the ugly side, look for opportunities to apply some of the things we've already seen. Maybe you can factor it. Maybe you can add fractions together. Maybe you can square stuff, depending, as long as it's top and bottom. Maybe you simplified the denominator. There's a million different things you can try, but there's some really common ones. Factoring, adding fractions are really common. Okay, beyond that, if you need to, you can look for places to use your fundamental identities, which means anytime you see something squared, top of your head, which trig identities? Anytime something's squared. I want you to think in the Pythagorean identities. Now, you want to be a little bit mindful of where you started and where you wind up or what you're trying to get to. Sines and cosines work really well together because they combine to be tangents and cotangents. Tangents and secants work really well together because things cancel out. Same with cotangents and cosecants. Okay, if you don't see any factoring or adding or any factoring, any combining into a single fraction type of stuff that's obvious, your last step to try something would be rewrite everything in sines and cosines. Like, maybe you need it, maybe you don't, but if you're struggling and you can't figure out any place to break in, that is a good route to go. And then finally, you have to try something. Do you think there might be a few proofs or verifications on our test at the end of the chapter? Probably. Like, I'll tell you, there will be. Now, when I grade proof and do the same thing in geometry, I expect two things from people. One, I expect you to always try. You should always try a proof. If you look at it and say, nope, I'm not even going to try it, then nope, you get nothing from it. If you try, pretty much always you're going to get half credit for it. All my proofs are worth 2 points. Did you try it? Like a real effort, try it. And did you get it right? Those are the 2 points that come in. You got to try something. Now, as we go through, other things that we'll see, we might run into it today, it might be tomorrow. The video tomorrow is essentially just going to be me talking and working through several examples, just so you're aware. So I'll go slow. Abigail or Kalisha, whoever's going to pause and stuff, I want you to pause it. And if you guys need to talk as a whole class, I want you to get ideas from everywhere as you're trying to solve this. If it gets too chaotic and is not helpful, obviously you guys know how to talk in here. Preferably more than you normally do, since I'm not here to talk with also, but I won't be here to tell, so I'll have to look at the video footage from the hidden camera. Anyway, here we go. I don't have a hidden camera, probably. All right, I want us to verify. This is our first example. Okay, in the off chance that you pick the wrong first step and you do 3 or 4 lines of work and it's terrible and you hate it and you've decided it's wrong, do not erase. X. Cross it out, because if you erase it and then try again later and don't remember what you did, you may very well do the exact same wrong thing again. Okay, here we go. Our first verification right off the bat. We want to show, and I'm going to say verify and show, ... I want to verify that secant squared x is a fraction. Secant squared x minus 1 divided by secant squared x equals sine squared x. So don't just blindly copy this proof for the proof that we're doing here, Riley, but if you want to see the guidelines so that Makisha can keep doing hers. We didn't write them down yet. That's as much space as it takes on the page. We talked about it. Yep. Okay. So, most importantly, I cannot multiply both sides by secant because they're not equal. We're trying to show that they're equal. So we need to pick a side. Which side is uglier? The left side. Are we all in agreement? So let's start with the left side then. I'm going to start here, and then I might do one thing to it if you want to, but we're going to use this side. Now, whatever I'm doing, I can, again, no properties of equality. Through a bunch of fancy stuff, I need to somehow transform this into sine squared. That's the goal here. So I'll rewrite just this side this time. Secant squared x minus 1 over secant squared x. As long as you take a step, you're going to be in the right direction. There's nothing in here that's going to be awful. If we get a few steps and realize it's not working, we'll just cross it out. We'll try a different first step. With that in mind, with what's on the board and all of these things here, we've already decided we're going to start with the complicated side. So number 2, is there anything that we can factor, add, square, simplify, anything along the way that you guys see the algebra says, yep, obviously we can do this? Say that again. Secant squared. Are you looking in the numerator or denominator? Okay, what would you like me to do with the secant squared in the denominator? So it's hard because I appreciate you volunteering. I love that you are. Talk with your neighbors for a second. Whether you agree with Bea to start there or not, it's entirely, dependent on your discussion. But I want you guys to talk and come up with maybe a couple approaches that we might try. Something to try. Something about secant squared is what I saw. What would you like me to do though?
Like 1, it would be 1 minus 1.
So it doesn't quite work like that because whatever we're going to divide, we have to factor out both. However, you could split it, and what you're trying to do is secant squared over secant squared minus 1 over secant squared.
Right.
So that doesn't quite change into 1 minus 1, but it does change into 1 minus 1. So I'm going to throw up a couple different ideas up here. This is Huggins' first idea, is split fraction. And Barcega, can you be a little more specific with what you said? So maybe we can change, you're looking at the denominator, right? Secant squared to 1 over cos squared. That's certainly an option at our disposal. Weird. Any other thoughts? Yep, so Pythagorean, there we go. In the numerator. Like, these are 3 completely valid approaches. Cool. I don't know which one off the top of my head is going to be the easiest. I know which one I would probably go with. Quick vote. Orange, purple? Green. Orange, purple, green. Shout it out. Oh, you got another idea. Okay, I heard green, Pythagorean theorem. Anybody second green? Okay, let's green it. All right, secant squared x minus 1 can be changed to what according to your Pythagorean identities? Tan squared x. Is that right? Tangent squared? Okay. Over secant squared. Okay. Now, I'm not going to require it at this point in time. If you guys are okay with not having to do 2 columns, I would like to avoid it. I need to have enough showing that anybody in class could conceivably pick up your page and understand what they're doing. So don't take like 4 line steps or 4 steps in 1 line between problems. Slow and steady wins this race. Okay, I have applied the Pythagorean theorem to just the numerator. I'm good with it. What next? So I could change everything into sines and cosines. Now, in this process, sure, I'm good with that. I might do one other thing real quick, and I actually will. Do you guys agree that this is the same as multiplying by 1 over secant? So whether I included this line or not, maybe it would be worth it, instead of calling this 1 over secant squared, that's the same thing as what? Cosine squared. And the note or the notation is secant squared x equals 1 over cosine squared. And I'm using the fact that I divided by 1 over cosine and it winds up flipping it. Okay. This was a part of that changing everything to sines and cosines. Now, always, always, always write the entire expression when you're doing your homework problems and stuff. Never just write half of it, because now that I'm pointing it out, you probably remember. But if this is all you wrote on your homework, because you're just starting the problem, you think it's possible you might lose track of where you're trying to end up? Write it down. Always write your show statement wherever you're trying to get to. Now, we've done this. I'm good with it. Could I change tangent squared into something else? It's sine squared x over cos squared x times cos squared x. Now, I'm annotating here with these stars. If we don't need it, like if your steps are small enough that you don't have to include it, I'm going to take your word for that. We just did, I'm not even going to justify that. I just changed tangent. I'm not going to write definition of tangent. We're not doing 2 columns. Anything else? If only there was something we could do to get to sine squared. Oh my gosh. We have just successfully taken the left side and only using algebra and trig changed it to sine squared x, which is what we just asked it to show, right? We didn't rely on any particular value of x. This is true for which values of x? All of them. Check it out. Last little piece that I want you guys to add. This box filled in indicates that this is the end of our proof. Now, if you look at this and think, I would not have done it that way, good. I'm totally good with that. This way works. If you want another example, whether you want it or not, I guess I'm going to show you, but you can write it down or follow along. It's entirely up to you. When I look at this problem, this is not the first thing that comes to my mind. It works. This is probably the second thing that comes to my mind. The very first thing that I notice is I can split this up using splitting this fraction. So I just want to see what happens if that's the step we take. And I don't know if this is going to be the right step or not, but we'll try. Let's just see if it works out any different. If I had taken this and split it up, do you agree that it's reasonable that I could say on my first line, once I've written this, I think it's going to be 1 minus 1 over secant squared x. Can you tell me how I've obtained that? Because if not, I'll show one more line of work. This is like not rhetorical, like legitimately, can you tell what I've done? Some people can, some people can't, and that's totally okay. How much work you show should be dependent on how well do you feel with it. If I wanted to split it up as a fraction, I know that if they have a single denominator, that could be split up with just two numerators in the same denominator. Like that's the same thing as in red on the left, right? What's secant over secant, or secant squared over secant squared? 1 minus, and now that I've written it out like this, I'm going to take one more step here too. 1 over secant squared is what? Cosine squared? And golly, sine squared plus cos squared is 1, which means 1 minus cos squared is, which is what we were asked to end up at. Two proofs of the same idea. Now, I'm not just trying to show you, like, look at all these options that are available. Every time that we see a different approach working, all that we're doing is reemphasizing the fact that, hey, there's a lot of ways to think about these, and maybe different angles are going to be applicable in different problems. This proof, easier or harder than the stuff that you did in geometry? Do these feel easier than geometry proofs to you guys? Interesting. Cool. Should we do another one together, or you want to try one on your own? Like together as a whole class. All right. Well, let's see. How about I give you a problem and then you guys determine. And actually, we'll split it. I'm going to give you 2 minutes to start it, and then we'll come back together and just draw on approaches. And I'll come around and look at what approaches you're making, and we'll find one. So for example, B. I want you guys to verify the following. It's another lovely fraction. We get cosecant squared theta minus cotangent squared theta divided by tan squared theta cosecant squared theta, tan squared theta times a cosecant squared theta. And I'm going to make the claim that this is actually equal to cosine squared theta. Now I'm going to pause it, but let's just make sure we all agree. Which side are we starting with? What'd you say? Which side's uglier? Start there. And I know it seems counterintuitive, but start here, and we'll talk about why after this problem. Okay, 2 minutes to try something. Don't care if you're on the right track or not. I bet you are if you try something that's like allowed. Try it out. I'll come around and steal some ideas. Okay, so checking this out. Here's the fun part that I like doing with this, and I'm really bummed that I'm not going to be here for the rest of the section in person. Whoever I call on first kind of picks the way that we go through the problem, right? Anybody want to volunteer to pick the start of the problem? And I'm not going to tell you whether I agree with it or not. We're just going to roll with it. If we decide to abandon ship, we'll abandon ship.
I already started splitting it.
All right, what do you mean splitting it?
I don't know if I even can, but I did 1 minus cotangent squared over tangent squared times cosecant squared.
So not quite like that. Can I see? Just because I think that.
I took the cosecant.
So you're close. I like your idea, but you split it up incorrectly. And like not throwing shade, but I have a single denominator and 2 very distinct pieces in the numerator, right? So we're going to split it. Anybody else's first step to split it up? Okay, I don't know if it'll work, but let's try it. Now, I'm going to take the time to like actually go through and really split it up. So we have cosecant squared theta over cosecant squared. I'm going to change the order just because it looks nicer in my head. Cosecant squared, tan squared. That's that first part. Minus what? Cotangent squared theta over the same thing, right? Cosecant squared, tan squared. So, here we go. Over itself. Look at it. It's beautiful. Well, I like it. Question. Are you sure? Because I'm pretty sure I heard you ask a question.
Well, why can't you just take cosecant? You can divide it out with a unit.
So, it's just like, so you're trying to do this, I assume. Yep, which I think is what I saw you try to do as well. But check it out. If I had, do you agree that 5 divided by 5 is 1? So let me think of how I can redo this. Okay, we're going to change it. 5 divided by 2 is 2.5. If I did, and I'm just checking, is 5 also 2 plus 3? So this still says 5 over 2, right? But if I do that, like you're suggesting, we get 1 plus 3 is 4. Like, it doesn't work, right? And I can see that it doesn't work. If you want to divide something out, you have to have it factored out of the numerator or standing alone. Easy, easy mistake to make. Okay, so we've done this. I see some nice things that happen. Now, do you is a bigger question. Charles, on this left one, right here, is there anything that can happen? They divide out and it leaves a what in the numerator? A 1. So let's see, we get 1 over tan squared theta minus, and then here's where I don't care if you do 2 steps in one, but make sure it's really clear and easy enough to follow. So 1 over tan squared theta minus, and now we have some decisions to make. Do we want to keep it as it is? Remember, we're trying to make it become a cosine squared, which I already see a cosine squared in the numerator. I can already see it. Not written, but it's there. Do you guys see where my cosine squared is? Where, Fern? My next step, this is going to become, if I wanted to, this is a cotangent, which is cosine squared over sine squared, and I already have a cosine squared up in the numerator at that point. Like, I can think ahead a little bit just by using these quotient identities. But we still got to deal with that other side. Thoughts? Change the cosecant to 1 plus cotangent. Okay? So you're looking at this cosecant and you're looking at using Pythagorean identity. Sure, let's try it. We get cotangent squared theta over, and you said 1 plus cotangent squared theta times tangent squared. Love it. That is a good substitution. Now, whether it works out or not, we'll see, but the fact that you're trying it, that's awesome. That's what I need. Okay, the left part, the 1 over tan squared. Do you want to just pull the trigger and call it cotangent right now? Okay. So this right here I know is cotangent squared. minus, and we still have that pesky right side. I'm open to suggestions. Okay, so let's think this out. This is really 1 over tangent, right? So if I distribute this through, I would get a cotangent squared to the numerator still. And then let's just see what shakes out here. That'd be a 1 times tan squared is tan squared. Plus, oh. What's cotangent squared times tangent squared? It's a 1. All right, so this is looking like, sorry? What's the Pythagorean? So I distributed here. If you were to take cotangent, and I'm just going to do cotangent, times a tangent, which is a 1 over cotangent, they're gone. It'll still happen with the squares. Why did I make the oh noise when I saw this? This is a secant squared. So, and again, we don't really know for sure if this is going to shake out. Nope. But we're trying. Now, I'm going to write secant squared here for this time. But on my next line, what might be worth doing, do you think? We got 30 seconds to finish this. Do you guys agree it feels like we're just walking, we're just taking steps without really knowing which way we're going? But as long as we take steps that are justified and valid, I bet we're going to wind up exactly where we need to be. I'm going to change this really quick, just in the interest of time. This is cosine squared theta over sine squared theta. Minus, and then cotangent squared, I know is cos squared over sine squared. And then this is multiplied by 1 over secant squared. Because dividing by secant is the same as multiplying by 1 over secant. But what's 1 over secant squared? It's what? Cosine squared. But check this out. This looks really terrible at first glance. We have a common denominator at this point though, right? Okay. I want you guys to finish this one, which I'm going to do one more step. This is a cosine to the 4th power. But if I factored out a cosine squared, I think it leaves behind a 1 minus cosine squared after it. I want you guys to finish this problem. The start of the video will be me concluding down this path and likely showing another alternative path. I want you guys to try to finish this tonight. Can't stress it enough. If and when you have questions about stuff, please email me. I will try my best. I'll be able to zoom in on Wednesday if I have to, I think. Maybe tomorrow, probably not. I'll be in the plane with a lot of you guys, actually. Cool. Later, Raiders. I will remind you all about Pi Day after spring break, and hope you all have a wonderful spring break. I will see you in a bit. Homework stuff, I'll decide how it's going to be.
Will you be here for sure?
Today, yeah. Yep. All right. Peace out, guys.